Hello and welcome to our video on satellites and free fall. Very interesting topic that we love to get into in physics. And hopefully by the end of this video, you'll be able to understand why satellites do not fall back to Earth. We know that gravity is pulling on these satellites, pulling them towards the Earth, but why do they not fall towards the Earth? So let's go ahead and dive right on in. So first off, let's look into what a satellite is. A satellite is any object, it could be man-made or it could be natural, that orbit another body like a planet or a star. So for instance, the Earth has the moon is constantly orbiting around the Earth, therefore the moon is technically a satellite. And satellites are actually in a constant state of free fall. So whenever something is falling, we call it free fall, and a satellite is in a constant state of free fall, but it never actually hits the Earth's surface because the trajectory of satellites are in a curved path, and we know that the Earth is a sphere, so the trajectory of these satellites are actually the same curved path as the Earth. So therefore, it's falling, but it never actually hits the Earth because it matches the curvature of the Earth. So let's look here. Hopefully I can visually show it to you. Let's say, for instance, we got you standing at the top of the Earth, and you want to throw a ball and try to throw the ball so hard that it goes into orbit. So you throw the ball, you throw it really hard, but it lands somewhere right here. So you can see that the path is somewhat of a curved path. It's somewhat, it leaves your hand and then it starts falling towards the Earth immediately. And, obviously that did not go into orbit. It ended up hitting the ground, and we don't want it to hit the ground. So you throw it harder. You throw it harder, and it looks like, oh man, it might go into orbit, but eventually it hits the ground again. But, you're standing way up here, and it goes over halfway around the Earth, but it still landed back on the Earth. So you throw it one more time, really, really hard, and it's falling towards the Earth, but you threw it at such a velocity that it's able to overcome the gravity and actually match the gravity. So it ends up coming back to its original spot. And after it comes back to its original spot, you know what it does? It just keeps going. It goes around again. And after it comes back to its original spot a second time, you know what it does a third time? It goes around again. So at this point, you've been able to throw the ball so hard that it actually went into orbit. Quick side note, nobody can throw a ball that hard. It's ridiculous. So, more about satellites. They move at in a horizontal velocity fast enough that the trajectory created by the Earth's gravitational pull actually matches the Earth's curvature. So you throw it so hard that the Earth is pulling on it as hard as it can, but it doesn't matter how hard the Earth pulls on it, the curvature of that object is going to match the curvature of the Earth. So that means that the trajectory of the ball that you threw is actually parallel to the Earth's curvature, or the trajectory of satellites is parallel to the Earth's curvature. So objects don't have to be in a straight line like so for them to be parallel. Objects can actually move in curved paths like this and still be parallel to each other because they never crossed. I know a lot of times we work with parallel objects like this, but that's not the only time an object is parallel. An object is parallel even if the object, or if the two lines do not cross and they're not straight. So, moving on. An object remains in orbit, and whenever it is in orbit, it is moving in a constant state of free fall, like I said, because the gravity is always pulling on it, but it never actually hits the ground. And for the Earth, an object must be moving at a velocity of 8 kilometers per second to orbit the Earth. That's not 8 kilometers an hour. No, this is 8 kilometers a second. That is moving very, very fast. and the satellites that are going around the Earth and the moon as it's going around the Earth are actually moving at extremely high rates of speed. Satellites cannot orbit very close to the Earth for multiple reasons, but the lowest a satellite can orbit the Earth is at 150 kilometers high. So 150 kilometers up in the air is the lowest altitude that a satellite can orbit the Earth. And the reason why is because if they're any lower, the satellite is going to be hitting a bunch of air molecules, and the friction between the air molecules and the satellite will cause the satellite to burn up because it is moving so fast. And now we're talking about free fall. An object experiences free fall when it only has the force of gravity acting on it. That means that there is no resistance that is being experienced on that object. So we have, let's say for instance, we have a sphere, and the only object that is working on it at this point would be gravity pulling the object down. So an object is in free fall when the only thing that is working on it is gravity. No air resistance or anything like that. And the acceleration due to gravity is negative 9.8 meters per second squared. Remember that. And this is a operation of Newton's second law. And now we're talking about terminal velocity. This is a term you might have heard before. Terminal velocity is when objects are not in a state of free fall because they are experiencing air resistance as they fall. Air resistance opposes gravity and acts in the upward direction. So the same example we just saw with a ball falling down towards the ground, and we know that gravity is working on it as it's falling, but there's all these air molecules in the way as the ball is falling. Therefore, those air molecules are hitting the ball and pushing the ball upward. Okay? So those air molecules are hitting the ball and pushing the ball in the opposite direction. And air resistance, so all those air molecules create resistance, and we call it air resistance, depends on two factors of the object. So the surface area of the object is very important when it comes to terminal velocity. And also the velocity of the object itself. So the faster the velocity is, the more air resistance that you have. So as an object falls, the air resistance increases until it equals the force of gravity, and we call that terminal velocity. So whenever an object, say for instance our ball, is falling down towards the earth with an acceleration due to gravity, but the air resistance is going up, and the air resistance is a force, and let's say for instance the force is 500 newtons. Let's say for instance the air is pushing up on this object with a force of 500 newtons, and the mass of the object and the acceleration due to gravity is also 500 newtons. So at this rate, the ball is still falling down, but it's not accelerating anymore. So the acceleration would equal 0 whenever something is experiencing terminal velocity because of all these air molecules that it's hitting. So it moves at a constant velocity. And terminal velocity is the fastest that the object can move due to the air resistance that the object is experiencing. So when air resistance equals the force of gravity, that means the object moves at a constant velocity, which is an example of Newton's first law, because the acceleration has stopped. So at this point, when the acceleration stops, the object has reached terminal velocity. So the faster an object falls, the more air resistance the object experiences. And whenever it's experiencing more air resistance, the net force decreases. So remember, whenever you have an object and you have multiple forces acting on it, say for instance a force down and a force up, you can add these forces up and you can get a net force. So for instance, let's say this one, the force is 100 newtons, and this force is 10 newtons, so the net force equals 90 newtons. So as an object experiences more air resistance, the net force decreases to a point where the two forces actually cancel each other out when we're dealing with terminal velocity. And also, as the net force decreases, so does the acceleration. So the acceleration decreases as the force decreases. So a terminal velocity example that we can look at is whenever an object that weighs 10 newtons falls to the earth. At first, it experiences its free fall. And so we know that the net force is 10 newtons and its acceleration is negative 9.8 meters per second squared. And then as the object falls, it experiences 4 newtons of air resistance. So that makes the net force of the object 6, because it started off with a 10 newton net force, and then it falls, hits air resistance. That air resistance works upwards at 4 newtons. Therefore, our net force would be 6 newtons. And the acceleration is now less than 9.8 meters per second squared because the air is pushing up, thus lowering the rate of acceleration, until a point where the object finally reaches air resistance of 10 newtons, and the net force would then equal 0. So the object was falling down with a force of 10 newtons the whole time, but eventually, as it keeps falling, it would reach terminal velocity because those air molecules are pushing up on the object with the same force of 10 newtons. So there will be no more acceleration. Yes, the ball is still falling, but it is not falling and speeding up anymore. It reaches a point to where it's just moving at constant velocity. Another example you can look at with terminal velocity would be dropping a rock and a feather at the same time. Now we know that the feather reaches its terminal velocity first because it has a lot less mass and it also has a greater surface area than the rock. So the rock is going to hit the ground first. So let's look at another example of terminal velocity right here, where the question is, how much air resistance acts on a 100 Newton bag of nails that falls at terminal velocity? So the bag is falling as fast as it can. I'm going to use this square shape to represent the bag of nails. And we know that it is falling and it has a force of 100 newtons. Now it's saying that it's falling at terminal velocity, which means these air particles are hitting the box at such a rate that the force of the air pushing up is equal to the force of the object falling down. So the arrow will go upwards, and that would mean that the force going upwards is 100 newtons as well, because terminal velocity means that the air resistance has equaled the force of the object itself. So for the answer to this question, 100 newtons.